Hi, my name is Ryan Pham, and this is my Lab 5 for Physics 2211. The lab was a choose your own adventure, so my adventure I chose was the Slinky problem. To introduce our lab, our purpose of this specific lab is to predict and analyze the motion of a slinky that is currently stretched out falling from rest. The two questions we want to answer is how does the slinky move? And does the bottom of the model slinky stay stationary just like how it does in the video? The fundamental principle was mainly based off of Newton's second law. Additionally, we must understand how to effectively use the gravitational force, the drag force, and tension force in our system. To do so, I created a model using the GlowScript software to replicate the experiment showcased in the video I used. The results of the lab showcase that more forces taken into account in our model results in a more accurate representation of the slinky falling. With Newton's second law, we know that our velocity update formula, or our v final, is equal to our v initial plus f net times change in t divided by m. We also know that our net force is equal to all the forces combined in our surroundings, which is the force of gravity, the force of drag, and the force that the top slinky has on the bottom. Since the slinky is dropped from rest, it has no initial velocity. Our gravitational force is states that W is equal to negative mg times j hat, with W being our weight force, m being our mass, g equaling our Earth's gravitational force, little g, which is 9.81 newtons per kilogram, and our j hat direction being 1 in the y direction, but our negative in our equation shows that it's going down towards the Earth. Our drag force, otherwise can be considered our air resistance in this scenario, is equal to negative the magnitude of v squared times v hat. Our magnitude of v is equal to our object speed, and our v hat is equal to our velocity direction. Our slinky force in this case would be the tension force, and this is turned into our applied force from the gravitational force at the top of the slinky when it reaches the bottom. Our system is the bottom of the slinky, and our surroundings would be everything else, which includes our gravity, drag, and the force from the top portion of the slinky onto the bottom. This is the video of the experiment I used.
One drop.
Wow, did you see that?
One drop.
This is my video analysis using Tracker. First, I set the height of the starting point as the calibration factor of the man Derek Miller. The axes were set at the top of the slinky to create an origin. And then I will take note that both lines were tilted by negative 0.3 degrees to offset the video being at a slight tilt. And based on our analysis, I recorded 12 equally spaced time intervals, and those were used to record the position of the bottom portion of the slinky. Analysis began with the mass at rest to have an initial velocity of 0, so right before he let go. This is the data that I gathered. My initial position vector is shown. Our initial velocity vector would be 0 meters per second since it started at rest. The duration of motion was 0.4 seconds, and our mass of the slinky was 0.25 kilograms. This is my model using GlowScript. Using the GlowScript model, we can simulate the movement of our slinky. So to compare this model with our video analysis, we must use the same mass, initial position, initial velocity, and length of the time the bottom slinky had stayed stationary, and then how long it was actually moving for. Then we add in our Newton's second law equations, our force equations, which include gravitational, drag, and tension, and our velocity and position update formulas. With this, we were able to conclude that our resulted model was pretty similar in replicating our experiment. It did have some irregularities of when the time would fall, and the experiment ended at y equals negative 1.73, while our model ended at y equals negative 1.93 meters, which are pretty close. Sources of error include the human error when using Tracker, which is probably why I had the time difference slightly off, and it also does not ideally consider all of the external forces that would occur in a very short amount of time. So to improve the experiment, we should use smaller time frames between each gathered data point and have a more inline camera angle. Thank you for watching.